All right, we are back from spring break and ready to get back to some blowing up. All right, so our first topic today is blowing up to extend morphisms. So let's recall that if we had a map, if we had a variety X, we could define a map to a projective space, let's say PR, by picking functions, regular functions f1 uh, through f0 through fr, and and then there's a map. The map's a point x just to the point with homogeneous coordinates f0 of x up to fr of x. Okay, and that was a good map. Now this map is well defined, not on all of x, but on x minus the vanishing locus of f0 through fr. Right, because if all the f's are 0, then we don't get a well-defined point of projective space. Okay, now this looks kind of similar to what we did when we were blowing up, and in fact, blowing up will give us a sort of a automatic way to extend this map to a different space to the blow-up. So let's recall how the blow-up works. So recall for the blow-up, to blow up this locus, the vanishing locus of f0 through fr, we just take the graph, right? I take the closure of the graph, closure of the graph. And what's the graph? The graph is the map from x to x cross PR that takes a point x to x, comma, and then the same map that we had before. Okay, and of course this is again x minus the vanishing locus of f0 through fr. Okay, and the point is, so we took that closure and we called that x tilde, and we also saw that the open subset x minus the vanishing of these functions you could consider as an open subset inside of x tilde, right? And x tilde itself is contained in this product, right? It's the closure of the graph in this product. And if we take the projection here down to PR, we now have a map from x tilde to PR, right? And I also claim that that is the same as the map. It agrees with the map here, right? So originally we had a map from here to here that was just that was this, right? And now we have a map from x tilde to PR that's just the projection. But when you do the projection, right, you're just chopping off this x and you just have these. So this is the same map as so this map here is basically the same map as this. But the point is now this map here is well defined on all of x tilde. So we have extended the map to all of x tilde. All right, so just to summarize, we started out with this map here. It was not defined on all of x. It was only defined on x minus this vanishing locus. If maybe you can't extend it to x, right? There might be some problem where with continuity or something, so it's impossible to extend it to all of x. But it is always possible to extend it to the blow up of x. I mean, why would you want to do that? I mean, maybe, for example, if x was a complete variety, you know, a projective variety or something, when you subtract out this vanishing locus, it's no longer complete, right? You have some missing stuff. But the blow up here, if x was a projective variety or a complete variety, then x tilde will also be projective, right? Because it's a closed subset of this. Okay, so we can extend it to x tilde, which is a complete variety. Okay. Let's do an example that kind of illustrates how this might work. So let's look at P1 cross P1. And And let's consider it with the Segre embedding in P3. And so remember, this is equal to the vanishing locus of x0, x3 minus x1, x2 inside of P3. Okay, so I think we've I think this is just the Segre embedding. I think we've talked about this this before, and let's blow it up. At the point 0, 0, 0, 1 in P3. Okay, so we'll pick our functions to be x0, x1, x2, and so we're blowing up at those functions there. And let me remind you that our original definition of blow up required us to pick regular functions here. These aren't regular functions, right? These are degree 1 homogeneous polynomials. But I think we had a remark that said that on a projective space it's okay to pick homogeneous polynomials of the same degree, and then you do the same construction and it works out just fine. Okay, so hopefully that's okay. Now what we want to do is compare this to this blow up here, and we're going to say that it turns out it's isomorphic to P2 blown up at 2 points. Okay, and let's give 2 specific points, 0, 1, 0, and 0, 0, 1. It doesn't actually matter which points you pick, because any 2 points can be taken to any other 2 points by some automorphism. So let's just pick these. All right, now the ideal of these 2 points, let's call these points A and B. The ideal of the points A and B is generated by well, y0, the first coordinate has to be 0, and then y1 times y2, meaning the product of the second 2 is 0, right? That determines A and B. Okay, now there's a problem here. We want to blow up at this ideal, but this ideal, we need generators all of the same degree. Remember, I made the remark here that if we want to use this blow up construction, we have to use functions all of the same degree. So this isn't quite right. So the thing that you want to use, so we'll use the functions y0 squared, y0, y1, y0, y2, and y1, y2. Okay, that's squared right there. All right, now it turns out these don't generate exactly the same ideal as this, but locally they give you the right thing. And the lope is a local construction, so this is going to be okay. So let's just check that on the affine chart. So when y1, for example, when y1 is not equal to 0, so that's going to be the chart that contains the point A. We have, well, we can take coordinates where we can normalize y1 to be equal to 1, and so then our ideal will be generated by y0 squared, y0, y2, and y2. Okay, and let's see, this we can go away because it's already generated here by this, and this can go away too. So it's just a y0 and y2, and that's exactly the point A that we want. All right, and similarly, you can check the same thing for the B. So to quickly review where we are, we're going to take P1 cross P1, we're going to blow it up at a single point here, and we're going to claim that that is isomorphic to P2 blown up at 2 points. And furthermore, we're saying that P2 blown up at 2 points We can do that by blowing up at these four functions here, even though they don't generate exactly the right ideal. If you restrict the affine charts, then they give you the right ideals. So it's the same thing. Okay. All right. So let's define the map that's going to give the isomorphism. So we have P1 cross P1 tilde is to blow up. Now that's contained in, well, I'm going to think of it as being in P3 cross P2. Okay, this P3 is just the P3 of the segregate embedding where P1 cross P1 is embedded. And this P2 here is the P2 corresponding to these three functions that you're blowing up at, right? Okay, and then over here we'll have a P2 blow up, and that'll be contained in P2 cross P3, where this P2 is just the same original P2, and this P3 here is corresponding to the four functions that we're blowing up at. Okay, and so now the map is easy to describe. We'll just take x0, x1. Well, actually, let me just write it like this. We'll just take a point of P3x and a point of P2y and map it to y, comma, x, right? All right, now this map from P3 cross P2 to P2 cross P3 is clearly an isomorphism, right? It just interchanges the two factors. Nothing interesting there. We want to know if it's inducing an isomorphism from here to here. So all we have to do is check that if you start with a point here, that it maps into here. We want to know if that's actually contained, if it actually lifts to a map here, right? And if this maps into here, and then the other way, if this maps into here, under this map here, then you'll know that it's an isomorphism, right? Okay, and in fact, we only have to check on a dense open subset of these things because this isomorphism here will preserve closures. Okay. Okay, so that's too many arrows, so let me erase that. So let's now start with the point x, y, in x, which now I'm considering as a subset of x tilde, which is a subset of. Okay, just for convenience, I think we're going to want to call this x here. So this vanishing locus inside of P3, let's call it x. So x is isomorphic to P1 cross P1, but I'm considering it as a projective subvariety of P3. All right. Okay, so this is here is x tilde. All right, let's consider a point, a little x inside of x, which is in P3, and let's assume that so it has projective coordinates like this, and let's assume that x0 is not equal to 0. Okay, so this implies that x is in x minus the vanishing of x0, x1, x2, right? Because x0 does not vanish, so it's not in this vanishing. And this thing here is considered as an open subset of x tilde, right? We know that because that's the construction of the blow-up. Okay, and furthermore, such x are dense in x tilde. Why is that? Well, the set of x's where x0 is not equal to 0, this is a not equal condition, so that'll be a dense open subset of x, and we also know that that this here is a dense open subset of this. Okay, so that's what we want. And now we need to think about how this point little x looks considered inside of x cross P2, right? And that's easy. That's just, it'll look like x0 dot 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 x3. You just take the same point here, and then in here, in the P2, you have to take the functions that you're blowing up at, the x0, x1, x2, right? Okay. Now, since x0 is assumed to not be 0 right here, we can take this point and multiply everything by x0 and still have the same point in projective space, right? Okay, and now I'm just going to rewrite all these coordinates here, except for this last one, x0, x3. I'm going to go back and use this equation here, this equation that defines x. It says that x0, x3 is equal to x1, x2. So we'll change this to x1, x2. All right, so what do we have now? So we started with a point xy here, xy, well, not an arbitrary, completely arbitrary point, but a point in a dense open subset, right? So we start with a point in the dense open subset here, and we mapped it, if we map it over here just by switching the coordinates, well, so we switch this and we get x0, x1, x2, comma, this thing, right? Or at least this equal to the same point as this thing. Okay, but what is this here? This is exactly a point, the blow up of P2 at the ideal generated by these things, right? So, right, these functions. The point is these functions here are exactly the things in this list right here. X2, x0 squared, x0, x1, dot dot dots. You can change them to y's if you want. Okay, so what have we done? We've checked that you take a dense open subset here, it is contained in this one over here. Okay, and the other direction is also not hard. So say you start with a point y0, y1, y2, and in the blow up the other point has to be y0 squared, y0, y1, y0, y2, y1, y2. Okay, and then if we kind of switch the points here, we want to know whether this thing lies on the vanishing set of x0, x1, sorry, x0, x3 minus x1, x2, right? But it's clear that it does, right? Because you just take this times this, and that's equal to this times this. All right, so so you get what you want. Okay. Oh, well, okay. And the other thing you want to check is the y0, y1, y2 over here. These are exactly the functions that you were blowing up on, right? So okay. Modulo, changing x's and y's to the right names. Okay, so that was kind of a nice proof. Algebraically, maybe it was kind of appealing because it came from a very simple map, but it's not very insightful geometrically, maybe. So let's try and think about the geometry a little more carefully. Let's go back to chapter 7 and review the Segre embedding of P1 cross P1, or at least the geometric picture of it. So it embeds as inside of P3, so you think of that as just like the space, right, with points at infinity that we can't really see, but just think of it as R3 is in space for the purposes of the picture. And P1 cross P1 has a ruling, so each of one of these lines is like a P1, and they cross nicely like this, and you can see the same ruling happening here on this surface embedded in P3. All right, so now let's keep that in mind. All right, now let's look at this picture here, which is going to kind of represent the map that we were just talking about. So here's our X isomorphic to P1 cross P1, and it looks like this surface here. We're going to project it down to the plane P2 by doing a projection from a point A. This is the point that we blew up, but we're not going to blow it up yet. We're just going to define this map. So for any point X on the surface, so here's an example X, you draw a line between A and X, and then that line will intersect this plane, this P2. Think of this P2 as being inside of P3. It will intersect this plane at exactly one point, and we'll call that f of x. All right, so that's our morphism. Now, of course, this morphism is not well defined at A, right? Because there's not a unique line between A and X. Now, we saw some examples where it was possible to extend the morphism. For example, if there was sort of a unique tangent line at A. Of course, in this case, there's not a unique tangent line at A because A is a point on a surface, so there's a tangent plane. There's lots of lines going through A. So that doesn't work. But that's exactly the sort of situation that the blow-up helps us with, because when we blow up the point A, we're basically replacing the point A with its the projectivization of its tangent space, the space of tangent lines at A. So now you know what the map is on the blow-up, right? On the blow-up, A is replaced with a space of lines through it, and so you take one of those lines and see where it intersects this P2. So maybe a tangent line like this goes down here, bang, and there's your map. All right, so that's exactly what you want. All right, and now let's think about the inverse and see what's going on there. So if you pick any point on this P2 down here, you can draw the line from that point up to A. So for example, let's do the f of x. Suppose you've picked this f of x. To find the inverse, you just draw the line from f of x up to A, and now this is a degree 2 surface, so you expect the line to intersect it in 2 points. So A is one of them, and the other point is exactly f of x, or sorry, is exactly x, which is the f inverse of f of x, right? Okay, now there's a couple places where this doesn't quite work. At these points at B and C, which we talked about before, there's a problem because the line through C and A, the whole line is actually contained in this surface, right? So it doesn't intersect at 2 points, it intersects in the whole surface. So that's a problem. Once again, though, blowups are exactly going to be the thing that resolves our problem. So you have one point here, and you sort of want to map the one point onto a whole line. But if you blow up this point, you sort of replace this point with the whole line, with the projected line P1, which then can map bijectively onto this line here. If you sort of want to see geometrically how that map works, so imagine a line through C here that corresponds to a point in the blow-up. So any point that's not right on C has a well-defined inverse. So then you just take the limit as you approach C along that particular line, and then you'll get the point that you want there. All right, so just to summarize, we had P1 cross P1, we had P2, we had a map between them, but there was a problem with the map at A. We blew up A and resolved that problem. There was a problem with the inverse map at B and C, but we blew up B and C and resolved those problems, and then the map became an isomorphism. All right, we are moving on to chapter 10 about smooth varieties. So first we need to recall something we talked about before, the tangent cone. So we are writing SC A of x to mean the tangent cone to x at A. And how did we define this, or how did we compute it? So the first thing we did is we assume that A is equal to the 0 point in some an, right? So how do you do that? Well, you have to pick an affine open set, affine open neighborhood of A contained in some an, and then maybe you need to do a change of coordinates to make A equal to the origin. Okay, and then the tangent cone was defined to be the vanishing set of the initial ideal, so the set of all f in, I think is what we called them, for f in the ideal of x inside of an. Well, I guess I should say inside the coordinate ring of an. Okay, and remember this f in means initial term, or in other words, the term of lowest degree. So, for example, x1 squared plus x0, x3. If you take the initial of that, you just get the x1 squared. Okay, and the tangent cone had a very nice geometric picture that's sort of easy to make sense of. So right here you see the tangent cone to this parabola. It's just the tangent line to the parabola. So if the variety is smooth, then the tangent cone is just tangent space. We'll say more about that later. In this case, where we had this node, where this double point, then the tangent cone was both of the tangent lines at each of the branches. And then you also had things like this this cusp, where this comes in and becomes tangent to this line, and the other one comes here. So the variety is not smooth at this point, but the tangent cone is still just this line here. All right. So now we're ready to define what the tangent space is. I've already said the word tangent space in this class, just using a kind of an intuitive idea, but now we're going to give the exact definition. So the tangent space. So let's let A be a point on a variety and assume it is the zero in some affine chart, just like we did before. And later on we'll talk about why it doesn't actually depend on which point you choose. Okay. Then the tangent space to x at A, I'll write t sub A of x, will be just the vanishing of f1, where f is in the ideal of x. Okay, and that'll be a subset of the an. All right, what is this f1? So f1 will just be the linear term. Okay, so for example, if I had the thing I had before, so 1 for, or I guess I'm using a subscript here. The linear term of that is just 0 because there's no linear terms. So something with an interesting linear term. If you take the 1 of that, you just get rid of the higher order things. You get something like this. All right. All right, and you can consider the tangent space either as just an abstract variety, or you could consider it, as a subvariety of an, where an is the same space that x is in. All right. Okay, and the other thing we should notice is that tangent space is isomorphic to an affine space, right? Okay, or in other words, you can think of that tangent space as a vector space. Why is that? Is it because it's the vanishing of just the linear polynomials? So I think maybe we talked about that very early in the class, that if you had the vanishing of some linear polynomials in an affine space, that will be isomorphic to an affine space. Okay, some remarks about the tangent space. So A is that you can take the linear terms of a set of generators. For I of x to get the tangent space. All right, so this is a contrast to the tangent cone. So I think we made a remark that for the tangent cone, it wasn't good enough to just take the initial terms of a set of generators to the ideal. You had to have you had to take all the initial terms of every element of the ideal, or some special set of generators like a Grubner basis or something. For tangent space, the situation is nicer. If you have some generators for your ideal, you can just take the linear terms of those generators, and any generators will work. All right, so that's good. All right, B is that you need to take the actual ideal of x, the radical ideal, right? Not just some equations defining x. All right, so this example to think about is suppose we had x equal the vanishing of x1 inside of a1, maybe versus y. Okay, versus x is also equal to, as a set, the vanishing of x1 squared in a1, right? And if you try and compute the tangent spaces here, you'll find that the tangent space at 0, there's only 1 point. At x here will be the vanishing of x1 in a1, so that'll just be a single point. So we're looking at the tangent space to a point, right? So that's exactly what we expect here. The zero-dimensional vector space, this is a single point. But the tangent space here, if you try to compute it this way, would be the vanishing of, well, the linear term here is 0, right? So this is equal to a1, a one-dimensional vector space. All right, so you didn't get the same answer. So we're not going to do this. Now, that's not actually a bug, that's a feature. When we talk about schemes, we'll interpret this vanishing set as a point with some non-reduced structure, and we really do want it to have a one-dimensional tangent space. Okay, but for now, we're going to stick with this. All right, and for part C, we should note that if the linear term of a function is not equal to 0, then it's clear that the initial term, f initial, will be equal to f1. Right? Okay, and I didn't mention this, but I should remind you that there's no constant term, right? Because we're assuming these functions vanish at the origin. Okay, this implies for us that the tangent space is always contained, or sorry, rather the tangent cone. The tangent cone of x is always contained in the tangent space. Right, every function that's defining the tangent space also applies to the tangent cone by this remark, but the tangent cone might have more things. All right, so let's go back to our examples that we were looking at earlier. So here's the case of the smooth parabola where the tangent cone, I said before, was equal to the tangent space, and that's exactly what you see here. The initial term here, the initial term is the same as the linear term, so everything's the same. Let's go look at this one. In this case, we have the tangent cone being the two lines here. We know that the tangent space is a vector space and the tangent cone is contained in it. So from that already, we know that the tangent space has to be the whole space. If you look at here, this generator has no linear term, or rather the linear term is 0. So according to our definition, the tangent space should be the vanishing locus of 0, which is everything. So that's what we get here. Now let's look at this third example. In this case, the tangent cone is a single line, so you might wonder if maybe the tangent space should also be equal to that line. But there's kind of a problem here, this singularity, this sharp point, which messes things up. So if you look at the algebraic definition, there's no linear term, or the linear term is 0. So again, the tangent space has to be the whole space. So the tangent space is not always just the span of the tangent cone. If there's like some kind of singularity like this cusp here, it might be bigger. The next thing we're going to do is prove a lemma that gives an alternate description of the tangent space that will eventually be useful when we're trying to prove that the tangent space is invariant of the coordinate patch that you chose. All right, so let me just write the conclusion, then we'll write down what the notation is. So it says that IA mod IA squared is isomorphic to the vector space homomorphisms from the tangent space to K, or maybe you like to write this as the dual of the tangent space. Right. Okay, and what are these things? So I of A is the ideal of the origin in X, which we're assuming is contained in AN. All right, so the ideal of the origin will just be generated by X1 bar through Xn bar. All right, so in AN, the ideal of the origin can be generated by X1 through Xn. X probably has some other equations defining it, so I'm writing these bars to show that these, I'm not thinking of them in the coordinate ring of X. All right, let's do the proof. We're going to define a map phi that takes the ideal of A, that's the ideal of the origin, and maps it to the space, the vector space homomorphisms in the tangent space to K, or in other words, the dual of the tangent space. And what is this map? Well, it's going to take an F bar and map it to the initial term of F, or rather the linear term of F, restricted to the tangent space of X. All right, so let's think about this and see if this makes sense. So given any F here, we can then lift it to an actual polynomial, and then we take the linear term of that polynomial, and now the linear part of that polynomial will be a vector space map from AN, right? It'll be a vector space map from AN to K. And then you just restrict it to the subspace, TAX, the subspace of AN here. Okay, and remember that this polynomial here vanishes at the origin, so it's actually and we're taking the linear part, so it's actually a linear map. Now the thing to worry about is whether this is well defined. So what we should think about what happens if G is in the ideal of X, then you know that the F bar is equal to F plus G bar, so we need to make sure those map to the same place. So F plus G bar would map to F plus G1 restricted to the tangent space of A. But F plus G, a linear term, is the same as the linear term of F plus the linear term of G, restricted to the tangent space here. And now the tangent space is defined exactly to be the places where all these G1s vanish, right? So this is just F1 restricted to the tangent space of A. Right, so G1 is an element, or sorry, yeah, G is an element of I of X, and the tangent space is defined to be the linear terms, the vanishing of all the linear terms of elements from the ideal of X. All right, so this map is well defined. Well defined. We should also note that it is surjective. Why is that? Well, any map from a subspace, the TAX to K, could be extended to a map from AN to K. Right? That's no problem to extend a linear map, and so you can just use that there. So I think it's easy to see it's surjective. All right. So now, if we want to prove the theorem, all we have to do now is check that the kernel is what we want. And what do we want? So we want to check that the kernel of phi is equal to the ideal of A squared. All right, so then we'll prove our theorem, our lemma by one of the isomorphism theorems. All right, so we just need the kernel to be equal to IA squared. One direction is pretty easy, so let's check that IA squared is contained in the kernel of phi. All right. So if f and g bar are both in the ideal of A, then f and g have no linear term, or sorry, have no constant term. All right, that's basically what it means to be in the ideal of A. But that would imply that f times g has no linear term, right? You know, the smallest degree term of f times g will be the smallest degree of f times the smallest degree of g, but there's no constant term, so there has to be like at least 2. But that's going to tell you that phi of fg bar will be 0 because there's no linear term when you take the 1 here. All right, so that shows you that the ideal of A squared is contained in the kernel. All right, let's do the other direction. Let's show that the kernel of phi is contained in the ideal of A squared. So first you have to make an observation. So let's define W to be the vector space consisting of all the linear terms of elements in the ideal of X. All right, and this will be a vector space, right? And it will be of some dimension, let's call the dimension K. And of course, the tangent space is by definition just the vanishing of W, right? The vanishing of all the polynomials in W. So it has dimension n minus k, where of course n is the dimension of an, right? Okay, so now let's look at the set of all linear forms that vanish on the tangent space. All right, so I'm thinking of linear forms on an that vanish on this subspace. And what's its dimension? Well, the dimension, of course, has to be a dimension k just by linear algebra. This is the complement of this. All right, but then the other thing we should notice is that W is contained in this space, right? And that's basically the definition of the tangent space is the vanishing of all the forms as defined by the vanishing of the forms in W. So W are some of those things. Okay, but now since W is also dimension k, so we get equality. Linear forms vanishing on TAX. All right, so let's now assume that we have some f bar in the kernel of phi, or in other words, what that means is that if you take f1 and restrict it to the tangent space, you get 0. So in other words, f1 is a linear form vanishing on TAX. So it's in W, right? And so that means there must exist some g in I of x, so that f1 equals g1, right? So that's by the definition of W and this equality here. Okay, then that tells me that f minus g has no constant term, but also has no linear term. All right, so if I look at f bar, well, f bar is the same as f minus g bar because this bar means, go mod ix, and g is in ix, right? But f minus g has no linear term, so that means it's in I of a squared. All right, so I started out with f bar, and now f bar is in the kernel, and now I know that it's in I of a squared, so we proved this. All right, so we're done with our lemma. So let me just review the statement. So the statement was you take I modulo I squared, and that will be equal to the dual of the tangent space. Okay, I think we're going to stop there for today, and I will return to smooth varieties on Friday.